Hello and welcome everybody to another episode of Books and Bytes. Today, we're diving deep into Marie Curie's radioactivity. It's her first-hand account of her pioneering research, published back in 1904. I have to admit, cracking open a scientific text from the early 1900s can feel a bit daunting. But this book is anything but dry.
It's true. It's more like reading Curie's lab notebook,
Mhm.
filled with her observations and experiments and even her struggles to understand this totally new phenomenon. It's really a fascinating journey through the early days of radioactivity research.
Exactly. And for a listener like you who's already familiar with the basics, we can really get into the nuances of her work. What I found fascinating is how Curie lays out the entire landscape of her research in this book. She tackles the three types of radiation, how they interact with matter, the challenges of measurement, the chemical effects, even the physiological effects, which, as we know, sadly took a toll on her own health.
It's remarkable how comprehensive her approach was. She wasn't just focused on isolating new elements. She was trying to understand the fundamental nature of radioactivity itself. And she did it all with such meticulousness and scientific rigor.
Okay, so let's start at the beginning. Curie's initial fascination with uranium and its mysterious rays is really the jumping off point for the whole book, right?
Absolutely. She starts by describing how certain uranium compounds, like pitchblende, were actually more radioactive than pure uranium itself. That was a huge clue that something else was going on, that there might be other, even more radioactive elements hidden within these ores.
It's like she stumbled upon a hidden doorway to a whole new realm of science. And her primary tool for exploring this realm was the electrometer, right? But I'm curious, how did she adapt this somewhat basic instrument to the challenges of measuring these elusive rays?
That's where her ingenuity comes in. Curie realized that she needed to create a highly sensitive and stable setup to detect the tiny electrical currents produced by ionization. She describes in detail how she modified the electrometer, using techniques like shielding it from external electrical disturbances and carefully controlling the temperature and humidity.
So it wasn't just a matter of pointing the electrometer at a radioactive substance and reading the dial. There was a lot of fine-tuning and problem-solving involved.
Exactly. And those challenges really highlight the resourcefulness of those early researchers. They were working at the cutting edge of science, often with limited tools and resources.
And speaking of challenges, how did Curie even begin to make sense of the different types of radiation being emitted? It wasn't like she could just see them.
Well, this is where her clever use of a magnetic field comes into play. She observed that these mysterious rays behaved differently when subjected to a magnetic field. Some were deflected in one direction, others in the opposite direction, and some weren't deflected at all.
And that's how she was able to differentiate between the three types of radiation, alpha, beta, and gamma, right? Each type responding differently to the magnetic field.
Precisely. It was a pivotal moment in her research, proving that these rays weren't all the same. They had distinct properties and behaviors.
So let's dive into these different types of radiation, starting with alpha rays. Curie describes them as positively charged particles, but they seem to have a rather limited ability to penetrate materials.
It's true, they're like tiny, heavy bullets that quickly lose their energy as they travel through matter. Curie uses a fascinating analogy in her book to explain this. She compares the absorption of alpha rays to the stopping power of a sheet of paper for a projectile.
It's a simple but effective image that really captures the essence of their limited range. But how did she actually demonstrate this experimentally?
One of her clever setups involved using lead blocks to create a narrow beam of alpha rays. She then placed a quartz piezoelectric device in their path to measure the tiny currents produced when the alpha rays struck it.
Now, I remember reading about this device, but it wasn't something you'd find in your average physics lab back then.
Definitely not. It was a rather specialized piece of equipment that exploited the unique properties of certain crystals to generate an electric current when subjected to pressure. Curie's brilliance was in realizing that she could use this device to detect and measure those tiny electrical signals produced by the alpha particles.
So she was essentially using this crystal as a microscopic microphone, listening in on the whispers of these invisible particles.
That's a great way to put it. And what she found was that the current generated by the alpha rays decreased as she moved the piezoelectric device further away from the source. Eventually, the signal disappeared, completely indicating that the alpha particles had reached their limit.
It's like they had a finite amount of fuel, and once they burned it all up, they simply vanished.
Exactly. And this concept of a range for alpha particles became a key element in understanding their behavior and their interactions with matter.
It's fascinating how Curie was able to extract such fundamental insights from these seemingly simple experiments. She was a master of observation and deduction.
Absolutely. And she didn't stop there. She went on to meticulously measure the range of alpha particles in different materials, exploring how factors like density and atomic weight affected their stopping power.
So she was building a comprehensive understanding of how these particles interacted with the world around them.
Precisely. And that knowledge would prove crucial for future applications of radioactivity. Everything from radiation therapy to the development of nuclear technologies.
Okay, so we've got alpha rays, those heavy short-range particles.
Hmm.
What about beta rays? How did Curie's investigation of them differ from her work on alpha rays?
Well, one of the first things Curie noticed about beta rays was their greater penetrating power compared to alpha rays. They could pass through materials that would completely stop alpha particles in their tracks. They were stealthier, you could say, more ghost-like in their ability to slip through matter.
Exactly. And this made them both more challenging and more intriguing to study. Curie couldn't just rely on simple absorption experiments like she did with alpha rays. She needed to develop new techniques to track their movement and measure their properties.
I can imagine. It's like trying to study the wind by observing the subtle movements of leaves, rather than feeling its direct force.
So how did she approach this challenge?
One of her key insights was recognizing the similarities between beta rays and another hot topic in physics at the time, cathode rays.
Ah, yes. Those mysterious rays produced in vacuum tubes that were causing quite a stir in the scientific community.
Exactly. And Curie, with her keen eye for patterns and connections, realized that beta rays deflected in a magnetic field, in the same way that cathode rays did.
So it was like she was piecing together a puzzle, using the knowledge of one phenomenon to illuminate another.
Precisely. And this analogy drawn by Curie herself was a major leap forward. It strongly suggested that beta particles were in fact high-speed electrons.
Wait a minute. So these mysterious beta rays emanating from radioactive substances were essentially the same thing as those tiny, negatively charged particles that were thought to make up atoms.
That's right. It was a revolutionary insight, connecting the seemingly disparate worlds of radioactivity and atomic structure. And this connection would have profound implications for the development of both fields.
It's like realizing that two seemingly unrelated threads in a tapestry are actually woven together, forming a more intricate, beautiful pattern.
That's a wonderful way to put it. And this discovery wouldn't have been possible without Curie's meticulous observations and her willingness to think outside the box.
Okay, so beta rays are essentially streams of high-speed electrons.
Yeah.
Got it. But there's still one more piece of the radiation puzzle, those elusive gamma rays.
Ah, yes. Gamma rays. These were the most penetrating of the three, capable of passing through even thick layers of lead. And unlike alpha and beta rays, they weren't deflected by magnetic fields.
So they were like invisible phantoms zipping through matter without leaving much of a trace.
Exactly. Studying them required even more ingenuity and creativity. Curie had to rely on indirect methods, like measuring the ionization they produced, as they passed through different materials.
So it was a bit like trying to study a ghost by observing the flickering lights and creaking doors it leaves in its wake.
That's a great analogy. And just as with alpha and beta rays, Curie meticulously documented her experiments with gamma rays, exploring their absorption properties and how their intensity decreased as they passed through various substances. She was building a comprehensive picture of their behavior, even though they remain largely invisible.
Okay, so we've got these three types of radiation, each with its own unique properties. But the story doesn't end there, right? Curie was also fascinated by the broader impact of radioactive substances on the world around them.
You're absolutely right. She dedicates a good portion of her book to exploring these fascinating effects, which extend far beyond just ionization and penetration.
Fill me in. What were some of the most intriguing things she observed?
Well, one of the most striking examples is her description of the luminescence produced by certain substances. When exposed to radium, she describes the eerie glow of these materials almost as if they were imbued with an inner light.
I remember reading about this. It's almost poetic, the way she captures the beauty and the mystery of this phenomenon. Didn't she even carry a vial of radium around in her pocket, marveling at its luminosity?
She did, and it's a powerful image, isn't it? This tiny vial containing a substance that could both heal and harm, glowing with an otherworldly light. It encapsulates the duality of radioactivity, its power, its beauty, and its potential for both good and evil.
It's like a scientific fable come to life.
Yeah.
A reminder that knowledge can be both a blessing and a curse. But Curie didn't just observe these effects, she tried to understand them scientifically, right?
Absolutely. She explored the chemical changes induced by radiation, the effects on crystallization processes, even the impact on biological systems. She was a true pioneer, venturing into uncharted territory and meticulously documenting her observations along the way.
Okay, so we've explored the different types of radiation, their unique properties, and their diverse effects on the world. But what I find truly remarkable is how Curie connected these discoveries to the very heart of matter, the atom itself.
Yes, this is where her work takes a truly revolutionary turn. Curie recognized that the source of this mysterious radiation lay within the atom itself, challenging the long-held belief that atoms were indivisible and unchanging.
It's like realizing that those tiny, seemingly solid building blocks of the universe were actually buzzing with internal energy capable of transforming and releasing incredible power.
That's a great way to put it. In Curie's meticulous observations of radioactive decay, the process by which radioactive atoms spontaneously transform, provided crucial evidence for this revolutionary idea.
I can imagine. It's like watching a tiny invisible fireworks display happening inside each atom, releasing energy and changing its very identity.
Exactly. And this realization opened up a whole new realm of scientific inquiry, leading to the development of nuclear physics and a profound shift in our understanding of the universe.
Okay, so radioactive decay, the transformation of atoms, the release of energy, it's all starting to come together.
Yeah.
But I'm curious, how did Curie go about measuring this decay? It's not like she could just watch atoms change in real time.
Well, this is where the concept of half-life comes in.
Ah, yes. The time it takes for half of the atoms in a sample to decay. But how on earth did she determine this? It's like trying to measure the lifespan of a mayfly.
It was an incredibly challenging task, requiring meticulous measurements and careful calculations. Curie had to track the decrease in radioactivity over time, accounting for any external factors that might influence her results.
So it was a bit like a scientific detective story,
Okay.
with Curie piecing together clues to solve the mystery of radioactive decay.
Exactly. And her persistence paid off. She was able to determine the half-lives of several key radioactive elements, including radium, polonium, and uranium, and those measurements became crucial for understanding the nature of radioactive decay and its implications.
So knowing the half-life of a substance allowed scientists to predict how long it would remain radioactive. That has huge implications, right?
Absolutely. That knowledge has been vital for everything from dating ancient artifacts to understanding the long-term impacts of nuclear waste. It's another example of how Curie's fundamental research has had a profound impact on our understanding of the world. But there's one more fascinating twist to this story: the concept of radioactive transmutation.
Wait, hold on. You're telling me that one element can actually change into a completely different element. That sounds like alchemy, not science.
It does, doesn't it? But that's precisely what Curie and other researchers were starting to uncover. They observed that as radioactive elements decayed, they would emit those alpha or beta particles, and in the process, their atomic structure would change.
So it's like those tiny nuclear reactors were spitting out particles and transforming themselves into different elements in the process. Mind-blowing.
It is. This process, known as radioactive transmutation, completely overturned the long-held belief that elements were fixed and immutable. It's like discovering that the periodic table isn't just a static chart, but a dynamic map of how elements can transform into one another.
It's amazing to think that Curie's work helped to reveal this fundamental truth about the nature of matter. And all of this from studying these invisible rays.
It's a testament to her incredible scientific vision and her relentless pursuit of understanding. But Curie's book isn't just about the science of radioactivity. It also reveals a lot about her as a person, her dedication, her struggles, and her profound awareness of the ethical implications of her work.
You're right, there are moments in the book where you can almost feel her grappling with the potential dangers of these powerful forces she's unleashed. She describes the burns she suffered from prolonged exposure to radium, and she emphasizes the need for caution and protection.
It's a reminder that scientific progress isn't always a smooth or straightforward path. It can come at a personal cost, and it carries with it a responsibility to use this knowledge wisely.
Okay, so we've explored the groundbreaking science, the challenges, and even the ethical considerations that emerged from Curie's work. But there's one more aspect I want to touch on before we move on to part 3, her writing style.
That's an interesting point. It's not what you'd expect from a scientific text from that era. It's surprisingly accessible and even poetic at times.
I agree. It's clear that she was not only a brilliant scientist, but also a gifted writer. There's a passage that really struck me where she describes the luminescence of radium with such awe and wonder. It's almost like she's describing a work of art rather than a scientific phenomenon.
You're thinking of the part where she says, "The radium shows a brilliant luminosity. The light emitted can be seen in broad daylight."
Yes, that's the one. It's such a vivid and evocative description capturing the beauty and mystery of radium.
Exactly. And those moments of poetic insight really add another layer to her work, making it all the more engaging and thought-provoking.
Okay, we've covered a lot of ground in this part, from the different types of radiation to the concept of radioactive transmutation, and even Curie's personal reflections on her work. But there's still so much more to explore. In part 3, I'm eager to dive into some of the specifics about the radioactive substances she studied, the challenges she faced in isolating and characterizing them, and the implications of her findings for our understanding of the universe.
It's going to be fascinating. We'll delve deeper into her meticulous experimental techniques, the surprising properties she uncovered, and the lasting legacy of her discoveries.
Stay tuned, folks. The adventure continues.
So let's talk about some of the specifics now.
Hmm.
About the radioactive substances that Curie studied. This was a time when the very concept of radioactivity was still new. So isolating and characterizing these elements was a huge challenge.
Absolutely. It was like trying to navigate a new city without a map, just relying on intuition and a few scattered landmarks. How did Curie even begin to approach this task?
Well, one of her first challenges was simply identifying which substances were actually radioactive. It wasn't always obvious. She meticulously tested hundreds of materials, carefully documenting her findings.
So it was a bit like panning for gold, sifting through countless samples to find those rare radioactive nuggets.
Exactly. And she didn't limit her search to just minerals either. She tested all sorts of things: chemical compounds, spring water, even plant ashes. Curie was determined to understand the full scope of radioactivity in the natural world.
Talk about a comprehensive approach. It's clear she wasn't afraid to get her hands dirty, both literally and figuratively. So which substances stood out as particularly intriguing?
Well, aside from uranium, which was already known to be radioactive, Curie's work led to the discovery of two brand new elements, polonium and radium.
Ah, yes. The discoveries that cemented her place in scientific history. But I recall reading that these elements weren't exactly easy to come by.
You're absolutely right. They were present in uranium ores in incredibly tiny amounts. We're talking less than a gram per ton of ore. Curie and her husband Pierre had to process huge quantities of raw material to extract even the smallest samples of these elusive elements.
It sounds like an incredibly daunting task. What were some of the key challenges they faced in isolating polonium and radium?
Well, one of the biggest hurdles was finding a way to track their progress. Remember, these elements were invisible to the naked eye, so Curie had to rely on their radioactive properties as a guide.
It's like they were using those invisible rays as a sort of chemical compass, pointing them towards those hidden elements.
Exactly. Curie would meticulously measure the radioactivity of each fraction of material she separated, carefully following the trail of increasing activity as she zeroed in on those pure elements. Her lab notebooks must have been filled with countless measurements and calculations.
It's a testament to her patience and persistence. So let's talk about polonium first. What made this element so special?
Polonium was the first new element Curie discovered, and it held a special place in her heart. She named it after her native Poland, a tribute to her homeland and a testament to her scientific brilliance.
That's a beautiful story. What were some of the key characteristics of polonium that she uncovered?
Well, she found that polonium was intensely radioactive, even more so than uranium. It primarily emitted alpha particles, those positively charged particles with a limited range.
And if I remember correctly, polonium's alpha rays were crucial in helping to understand the nature of radioactivity itself.
Absolutely. Curie's meticulous experiments with polonium's alpha rays led to the concept of a specific range for these particles, a key step towards understanding the particulate nature of radiation. It was like she was piecing together a puzzle one experiment at a time.
Okay, so polonium, intensely radioactive, primarily an alpha emitter, and a key player in unraveling the secrets of radiation.
Got it. Now, what about radium? What made this element so remarkable? Radium was arguably Curie's most famous discovery. And for good reason. It was even more radioactive than polonium, emitting a powerful mix of alpha, beta, and gamma rays.
And didn't radium's intense radioactivity have some pretty dramatic effects? I remember reading about it causing objects to glow and even producing heat. It sounds almost magical.
It does, doesn't it? Curie describes these phenomena in vivid detail in her book. She even mentions that radium salts felt warm to the touch, a clear sign that they were releasing energy.
It must have been both awe-inspiring and a bit frightening to witness firsthand. Did Curie delve into the chemical properties of radium as well?
She did. She discovered that radium behaved chemically very similarly to barium, another element in the same group on the periodic table.
So even though it possessed these extraordinary radioactive properties, radium still followed the basic rules of chemistry.
Precisely. And that observation was crucial for understanding how radioactive elements fit into the broader framework of chemistry. It demonstrated that the periodic table wasn't just a chart of elements, it was also a map of their relationships and how they behaved.
It's another example of how Curie's work helped to bridge the gap between the old and the new, connecting these revolutionary discoveries about radioactivity to the fundamental principles of chemistry. But let's not forget about the cultural impact of radium.
You're right. The discovery of radium sparked a sort of radium craze in the early 20th century. People were captivated by its glowing properties and its potential. Though not fully understood applications, it was added to everything from toothpaste to cosmetics.
It's a bit unsettling to think about now, knowing the dangers of radiation. But back then, the risks weren't widely known. It's a reminder that scientific discoveries, even those with great promise, can have unintended consequences.
Absolutely. It highlights the importance of approaching scientific advancements with caution and a healthy dose of skepticism. But despite those early missteps, radium's legacy is ultimately one of scientific and medical progress.
Curie's groundbreaking work on radium paved the way for countless advancements in medicine, our understanding of the universe, and even everyday technologies. It's a true testament to her enduring impact on the world.
It is. It's fascinating to see how her meticulous research conducted over a century ago continues to shape our world today.
It has been an incredible journey exploring the world of radioactivity through Curie's eyes. We've learned so much about her groundbreaking discoveries, the challenges she faced, and the lasting impact of her work.
And we've only just scratched the surface. Curie's book is a treasure trove of insights and observations. It's a reminder of the power of scientific curiosity, meticulous experimentation, and the enduring legacy of a truly remarkable mind.
Thank you for joining us on this deep dive into radioactivity. We hope you've enjoyed this exploration of Curie's groundbreaking work, and that it sparked your own curiosity about the wonders and complexities of science.
Until next time, keep exploring, keep questioning, and keep seeking those aha moments that make the pursuit of knowledge so rewarding.